Good day, everybody. We have a problem that depends on a ceiling function, which is actually quite a small part of the problem. So let's talk about what the ceiling function does. It's the least integer function, and compare that with the greatest integer function, which is referred to when you're referring to the floor function. But the ceiling of any real number is the least integer that's greater than the input argument. Okay. So you'll notice right here, 22 over 3 is between 6 and 7, right? It's between 6 and 7, so its ceiling is going to be 7. No, excuse me. I said that wrong. It's going to be 8, isn't it? Right, folks? And the reason is 22 over 3 is between 7 and 8. Okay. And just for definitional purpose, I'll put less than or equal to 8. Okay, so again, 22 over 3 is a number that's trapped between 7 and 8. So the least integer greater than 22 over 3 is certainly 8. Okay, now again, that's just definition of the ceiling. Now what we're going to do right now is, the big part of this problem, of course, is to find the ceiling of this sort of infinite geometric series. It's not really a geometric series in form, but you have the 1/2 here that's going to go to 0 really, really fast. So you anticipate some convergence here. Now let's give this thing a name. Let's give this part right here, so we don't have to keep writing. Now let's give it a name. Let's just call it S. All right. Now, so let's write down S in a more explicit form. And right here, folks, if I is equal to 0. If you put I equals 0 right here, you certainly get 1. Anything to the 0 is 1, and then you have a 1 right here. So that's 1. Now, if I is 1, if the index is 1, if you put a 1 right here, you do get the 3 you see. And then you have 1/2 quantity squared, which is 1/4. In a similar fashion, you can see that for I equals 2, you get 5 over 16. I equals 3. I equals 4, you get these terms that you see. Okay. Now, the trick on this sometimes is to go far enough out. I think I did for this. Now, this next step is kind of unmotivated. It depends on you if you happen to know the formula for an infinite geometric series, which I'll write down here in a bit. But this very next step would be something that would be difficult to find for somebody who wasn't familiar with infinite geometric series. Even if you are, it's not real clear why this works. But I looked at the solution. I wouldn't have known to do this. Now, so you multiply the original series by 4, and you get this. It looks slightly more palatable. Now, the goal is to do some manipulations that will get it to look like a geometric series. And that's what all of this does, folks. If you multiply for S by 4, you get this statement right here. It's still not quite a geometric series because you can't multiply one term and get to the next term. For example, there's no fixed constant or common ratio that you can multiply. So these kind of manipulations you're trying to find a common ratio. All right, and right here we see that if we subtract S away from this, we do have a common ratio. All right, I don't think we had the common ratio right here, but if you subtract S away from it, we end up with a common ratio. And yeah, let me just, I'm leaving just a little bit out right here. This part right here is 3S, right? So what I did is divided this whole thing by 3. 6 divided by 3 is 2. 1/2 divided by 3 is 1/6. This is 1/8 divided by 3 is 1/24. This is 1/32 divided by 3 is 1/96. Now the benefit to this, folks, is that this part right here happens to be a geometric series because 1/4 times 1/6 is 1/24. 1/4 times 1/24 is 1/96. So you see, we do have what they call a geometric series. Let me just briefly write down that it's a fairly easy thing to work with. This involves limits, but we don't have to worry about that as far as the formula. Let F be the first term. Okay, and then we'll have 1 minus R down here. Now, R represents the common ratio. For this particular problem, the common ratio is 1/4. So R would be 1/4 right here. And y'all, I'm just looking at 2's just sitting there. We can add that at the end once we do this. Okay, but R is 1/4. It's a common ratio. And again, the common ratio, they call it common because you can get from one term to the next by multiplying by the common ratio. Not sure why the marker quit working on me. Okay, folks, this right here is 1/4. Okay. Now again, 1/4 times 1/6 is 1/24. 1/4 times 1/24 is 1/96. Okay, but this is what, and again, the proof of this isn't particularly difficult. It involves a very routine limit statement based on the fact that r is less than 1. But this would be of the form f first term plus fr plus fr squared. And you see you're getting from one term to the next by multiplying by r. Okay. Now, let me put the dots here to indicate it goes on and on. Okay. So what we have right here, ladies and gentlemen, is just this right here. 2 is going to be a constant we'll add to the calculation. So it's going to be 2 plus, the first term is 1/6. Okay. And it's divided by 1 minus 1/4. Okay, so this is equal to 2 plus 1/6 over 3/4. But dividing by a fraction is the same as multiplying by its reciprocal, right? And so this would end up being equal to 2 plus, folks, now I'm going to do a little bit here. I'm running out of room. Think of 4 over 3 being multiplied by 1/6. So that would be 4 over 18, right? But 4 over 18 reduces to 2/9. Okay? Okay? And so you see this is our S, right? So let me come back up here. This is our S, 2 and 2/9. And so what will happen right here, what do we got? We have just shown that this is equal to the ceiling. And this is very explicit. There's no need to write this as a proper fraction or improper fraction. 2 and 2/9 explicitly, okay, 2 and 2/9, some people would prefer to write just 2 plus 2/9, okay, rather than try to remember these mixed fraction form things. But so this is 2 plus 2/9. And of course, the greatest integer, or the least integer that is greater than this number is 3. Okay, so that's the answer. Okay, and y'all, that's it. So again, it's kind of by the way, y'all, a problem similar to this was SMO Open back in 2023. I'll put some more about that in the description. But anyway, I think they did the floor of it. Okay, but it's essentially the same problem, except I did the ceiling. And there's a recommended way that depended on a Taylor series, they wanted the problem writer wanted you to use a Taylor series expansion 1 over x minus 2 quantity squared. But this way was something that was shown by Wei Tan, who works in Singapore as a math coach, I think. And he recommended this approach right here. It doesn't require a whole lot of knowledge other than just knowing that a method like this would work and just having to know the form for a geometric series. Okay? But anyway, this is... I guess that's it. We got S is equal to 2 and 2/9. And S is equal to this. So we have the ceiling of 2 and 2/9, and the answer is 3. Okay.